The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, let's get started. So today we start out geometric data structures. There are two lectures on this. This is lecture 1. And we're going to solve two main problems today. One is point location, which is finding yourself in a map. And the other is orthogonal range searching, which is catching a bunch of dots with a rectangular net. And they're fun problems, and they're good illustrations of a couple of techniques. We're going to cover two general techniques for data structure building. One is dynamizing static data structures, turning static into dynamic, using a technique called weight balance, which is really cool. And another one's called fractional cascading, which has probably one of the coolest names of any algorithmic or data structures technique. It's actually a very simple idea. It sounds very scary. And with point location, we're going to see some fun connections to persistence and retroactivity, which was the topic of the last two lectures, you may recall. And so we'll start out with that. Planar point location. You can do it in higher dimensions as well. In general, geometric data structures are about going to more than one dimension. Most data structures are about one-dimensional ordered data. Now we have points in the plane. We might have polygons in the plane. So this is what we call a planar map. Got a bunch of line segments and points forming a graph structure. So think of it as a planar graph drawn in the plane where every edge is a straight line segment. And none of the edges cross, let's say. So this is a planar map. It's also called a planar straight line graph. And the static version of this problem, so there's two versions. One is static. You want to pre-process the map. So I give you a single map up front, and then I want to support dynamic queries, which are which face contains a point P. So that point P is going to be given to you as coordinates, x and y. So maybe I mark a point like this one. I give you those x and y coordinates. I want to quickly determine that this face is the one that contains it. Give you another point over here, quickly determine it's this face. This has a lot of applications. If you're writing a GUI and someone clicks on the screen, you need to map the coordinates that the mouse gives you to which GUI element you're clicking on. If you have a GPS device and it has a map, so it's pre-processed the map all at once, and now given to GPS coordinates, latitude, longitude, it needs to know which city you're in, which part of the map you're in, so that it knows what to display, that sort of thing. These are all planar point location problems. It comes up in simulation, lots of things. This is actually one of the first problems I got interested in algorithms way back in my oceanography days. So that's planar point location. That's the static version. The dynamic version, make things harder, is the map is dynamic. So here the map is static. The queries are still coming online. Dynamic version, you can insert and delete edges in your map. And let's say if you get a vertex down to degree 0, you can delete the vertex as well, add new degree 0 vertices. As long as you don't have crossings introduced by inserting edges, you can change things. So that's obviously harder. And we can solve this problem using persistence and using retroactivity in a pretty simple way. Using a technique which you may have seen before, pretty classic technique in computational geometry. So this is a technique that comes from the algorithms world, and we're going to apply it to the data structures world. So sweep line technique. It's a very simple idea. Say you have some line segments in the plane. Something like this. And I'm going to take a vertical line. So the algorithmic problem is I want to know, are there any crossings? Do any of these segments cross? This is where sweep line technique comes from, I believe. So the idea is we want to linearize or one-dimensionalify the problem. So just take a slice of the problem with a vertical line and imagine sweeping that line from left to right. So it's going to, you imagine it moving continuously. Of course, in reality, it moves discretely. Let me unambiguate this a little bit. Okay, there are discrete moments in time when what is hit by this sweep line changes. Initially, let me maybe label these segments. We've got A, B, C, and D. So initially we hit nothing, then we hit A, then we hit B. Why do we hit B? Because we saw the left endpoint of B. Then we see the right endpoint of A, which means we no longer, at this point we see both A and B in that order. Then we lose A, so we're down to B. Then we see C, C is above B. Then we see D, D is above C and B. Then C and D cross. So C and D change positions. And then we have B. Then we lose B. Then we lose C. Then we lose D. Okay, this is the classic algorithm for detecting these intersections. I don't want to get into details how you do this, but you're trying to look for when things change in order in these cross sections. And the way you do that is you maintain the cross section in a binary search tree. So you maintain the order. If you hit a left endpoint, you insert into the binary search tree. If you see a right endpoint, you delete from the binary search tree. And you do some stuff to check for crossings. In this problem, there are no crossings, so we don't need to worry about that. Okay, but we're taking this technique. Say, okay, there's a data structure here, which is the binary search tree maintaining the cross section. Okay, so typically, the cross-section data structure is a regular balanced binary search tree. Our idea is, what if we add persistence to that binary search tree? So instead of using a regular binary search tree, we use a partially persistent balanced binary search tree, which we know how to do. This is a bounded in-degree structure. We can make it partially persistent, constant overhead. So if we add partial persistence, what does that let us do? Well, it lets us look at a moment in the past. Partial persistence is about querying the past. So there's a sequence of insertions and deletions that occur from the sweep line. But now if we can query in the past, that's like going to a desired x coordinate and saying, what does my data structure look like at this moment? Okay. Now the data structure, let's maybe look at this one because it's got 3 elements, very exciting. So you've got D, then C, then B. So you've got a little data structure. It looks something like this. It understands the order of the cross-section of those segments. And so, for example, if I was given a query point like this one, I could figure out what is the segment above me, what is the segment below me. That is a successor query and a predecessor query in that binary search tree. Okay, so a query, this notation maybe, a query at time t of, let's say, successor of y is what we call an upward ray shooting query. From coordinates t comma y. So t, the time, is acting as x coordinate. This time is left to right here. And so what's happening is we're imagining from this point shooting a ray upward and asking what is the segment that I hit first. That's an upward ray shooting query. And this is from a problem called vertical ray shooting, which is more or less equivalent to planar point location. So vertical ray shooting, again, you're given a map, planar map, and the queries are like this. What is the first segment that you hit with an upward ray? So I give you a point, x, y, and I ask if I go up from there, what's the next edge that I hit? That's a vertical ray shooting problem, and we just solved the vertical ray shooting problem. For static. If you're given a static map, you run this algorithm once, assume there are no crossings. Then to answer a vertical ray shooting query, we just go back in time to time t, do a successor query, which takes log n time, and then we get the answer to this. So we can do this in log n per query, static. This is all two-dimensional. I should probably say that. You can generalize, but questions? This is actually really easy. This is the stuff we get for free out of persistence and, in the moment, retroactivity. I believe this is one of the reasons persistence was invented in the first place. There were a bunch of early persistent data structures. Then there was the general Driscoll paper, which I talked about. But I think this geometry was one of the main motivations, because it lets you add a dimension as long as that dimension is time-like, then you get the dimension sort of for free. So that's nice. Okay, what about retroactivity? Again, we're going to use partial retroactivity. And I can tell you for certainty, because I was there, this is why retroactivity was invented. So retroactivity. So that would mean that we get to dynamically add and delete insertions and deletions. So that's like adding and deleting segments from this structure. Again, we have a linear timeline. We always want to maintain a linear timeline because that is reality. That corresponds to the x-coordinate. And now I want to be able to add a segment like this, which means there was an insertion at this time, a deletion at this time. Now, this doesn't quite work because this point in cross-section is actually moving over time. Binary search trees, that's okay, because things are simple. But at the moment, all we know how to do is actually horizontal segments, which are inserted and deleted at the same y-coordinate. So then we can do insert, let's see, at time t1, an insertion of some y-coordinate, and then an insert at some later time, the deletion of that y-coordinate. So this is a partially retroactive successor problem. This is equal to dynamic vertical ray shooting. Or I guess this insertion corresponds to the insertion of a thing. If you instead do delete here, then you're deleting one of the segments. This is among horizontal segments. So if your map is made of horizontal and vertical segments, so it's an orthogonal map, then you can solve the dynamic problem using a partially retroactive successor. Again, we want to do successor, just like before, query in the past, but now our updates are different. Now we have retroactive updates. That lets us dynamically change the past, which is like inserting and deleting edges through that algorithm. But at the moment, we only know how to do this for horizontal segments. So this gives us, if you remember the retroactive successor result, we haven't seen that, how it works. It's complicated, but it achieves log n insert delete successor retroactively. And so we get a log n, which is an optimal solution for dynamic vertical ray shooting among horizontal segments. There are a bunch of open problems. What about general maps? So for dynamic vertical ray shooting, in general maps, the best result is, if you want log n query, the best results are log to the 1 plus epsilon insert, log to the 2 plus epsilon delete. There's some other trade-offs. You can get log times log n query and reduce. Still, we don't know how to do deletes faster than log squared in any of the general solutions. So you can do log squared for everything, but the hope would be you could do log for everything, even when the segments are not horizontal. But here, retroactivity doesn't seem to buy you things. Be nice if you could. Another fun open problem is, what about non-vertical rays? General rays.
You mean non-horizontal?
Non-vertical rays.
Oh, sorry.
So what if I can now query, I give you a point and I give you a vector. I want to know what do I hit in that direction. This is a lot harder. You can't use any of these tricks. And in fact, it's believed that you cannot get polylog performance unless you have a ton of space. So the best known result is, just throw this up here, you can get n over square root s polylog and query if you use basically s space. So you need quite a bit of space, because if you use like n to the 1 plus epsilon space, you can get roughly root n query time. If you use n to the 5 space, then you get somewhat better query time, but still not great. You can maybe get down to n to the epsilon if you have very large polynomial space. But this is conjectured to be roughly optimal, I assume, other than the polylog factors. Belief is you cannot beat this for general rays. This is kind of annoying because this is a problem we care about, especially in 3D. This is ray tracing. You shoot a ray, what does it hit? It bounces. You shoot another ray. I always want to know what objects am I hitting. And there are lots of, for special cases you can do better, but in general it seems quite hard. This is even in 2 dimensions. But there are a bunch of papers on 3D and so on. I just wanted to give you those connections to persistence and retroactivity, and that's point location. And now I want to go on to orthogonal range searching. We can do some new data structures, new to us. So first, what is the problem? So it's sort of the reverse kind of problem. Here you're given a bunch of points. Before the query was a point. And the query in this case is going to be, in 2 dimensions, a rectangle, a window, if you will. And you want to know what points are in the rectangle. So given n points in d dimensions, query in general is going to be a box. So it's in 2D it's an interval across an interval. In 3D it's 3 intervals cross product together. Okay, so in the static version you get to pre-process the points. In the dynamic version the points are being added and deleted. And in all cases we have dynamic queries, which are what are the points in the box. Now there are different versions of this query. There's an existence query, which is are there any points in the box? That's sort of the easiest. Next level up is how many points are in the box, which you can use to solve existence. Next level up is give me all the points in the box, or give me 10 points in the box, give me a point in the box. All these problems are more or less the same. They do differ in some cases, but the things we'll see today, you can solve them all about as efficiently. But of course, if you want to list all the points in the box, it could be everything, and so that could take linear time. So in general, our goal is to get a running time something like log n plus k, where k is the size of the output. So if you're asking how many points are in there, the size of the output is a single number. So k is 1, you should get log n time. If you want to list 100 points in there, k is 100, and so you have to pay that to list them. If you want to know all of them, well then k is the number of points that are in there. And we'll be able to achieve this, these kinds of bounds pretty much all the time. Definitely in 2 dimensions. In d dimensions, it's going to get harder. Okay. So I want to start out with 1 dimension, just to make sure we're on the same page. And in general, we're going to start with a solution called range trees, which were simultaneously invented by a lot of people in the late 70s. Bentley, one of the main guys. And in general, we're going to aim here for log to the d n plus k query time. So like this, but now we have a dependence on dimension. And for 2D, this is not great. It's log squared. And we're going to do better. Okay, but let's start with d equals 1. How do you do this? How do I achieve log n plus k query? Sort the points. Yeah, I could sort the points, then do binary search. So the query now is just an interval. That's the 1-dimensional version of a box. So if I search for A, search for B in a sorted list, then it's all the points in between. I can count the different indices, or subtract the 2 indices into the array. That'll give me how many points there are in the box, all these things. Arrays aren't going to generalize super nicely, although it is actually, we'll come back to arrays later. For now, I'd like to think of a binary search tree, a balanced binary search tree. And I'm going to make it a little different from the usual kind of binary search tree. I want the data to be in the leaves. So I want the leaves to be my points. And this will be convenient for higher dimensions. Doesn't really matter for 1 dimension, but it's kind of nice to think about. So you've got a binary search tree, and then here is the data sorted by the only coordinate that exists, the x coordinate. And so, of course, I can search for A. Here's A, maybe. Search for B. And the stuff in between here, that is my result. And a little more detail, as you search for A and B, at some point, they will diverge. One will go left, one will go right. At some point you reach A. Maybe A isn't actually in the structure. You're searching for everything between A and B inclusive, but A may not be there. So in general, we're going to find the predecessor and successor of A. In this case, I'm interested in the predecessor. And similarly over here, eventually I find, this is all, of course, logarithmic time, I find the successor of B. Those are the 2 things I'm interested in. And now all the leaves in between here, that's the result. Question?
So if you have the data just on the leaves, what do you have in the intermediate nodes?
Right. So in the intermediate nodes, I need to know, let's say, if every subtree knows the min and the max, then at a node I can decide, should I go left, should I go right? I think every node could store the max of the left subtree if you just want 1 key per node. But yeah, good question. Sorry, I forgot to mention that. You store one of a representative sort of in the middle that lets you decide whether to go left and right. So you can still do searches. We can find these 2 nodes. And now the answer is basically all of this stuff. I did not leave myself enough space. That's a left child. Okay, so wherever this left branch went left, the right branch is in the answer. Whenever this right branch went right, the left branch is the answer. But from here, there's no subtree that we care about, because this is all greater than what we care about. Okay, but the good news is there's only log n of these subtrees, maybe 2 log n, because there's the left side, the right side. Okay, so the answer is implicitly represented. We don't have to explicitly touch all these items. We just know that they live in those subtrees, and there's order log n subtrees. So in particular, if every node stores the size of its subtree, then we can add up these log n numbers and we get the size of the answer. If we want the first k items, we can visit the first k items here in order k time. Okay, so in log n time, we get a nice representation of the answers, log n subtrees. Of course, we also had a nice answer when we had an array, but this one will be easier to generalize. And that's range trees. So that was a 1D range tree. The only difference is we put data at the leaves. 2D range tree has a simple idea. We have the data in these subtrees. These are the matches. Let's think we have x coordinate and y coordinate. We have an x range and a y range. Let's do this for x. Now we have a representation of all the matches in x. So we want this rectangle. But we can get this entire slab in log n time, and we have log n subtrees that we now have to filter in terms of y. There's all these points out here that we don't care about. We want to get rid of those and just focus in on these points. So we're going to do the same thing on y, but we want to do that for this subtree, and we want to do it for this subtree, and for this subtree. So a simple idea, for each subtree, let's call it an x subtree. So we have one tree which represents all the x data. It looks just like this. And then for each subtree of that x tree, we store let's say a pointer to a y tree, which is also a 1D range tree. So this guy has a pointer to a similarly sized triangle, except this one is on y. This one's sorted by x, this one's sorted by y. Same points. Okay, this subtree also has one. Same data as over here, but now sorted on y instead of x. For example, there's a smaller tree inside this one. That one also has a pointer to a smaller y tree, except now these are disjoint because these are completely, this is a subset of that one. But we're going to store a y tree for this one and a y tree for this one. So we're blowing up space. Every element, every point lives in basically log n y trees. Okay, because if you look at a point, there's the tiny y tree that contains it bigger, 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 bigger until the entire tree also contains it. Each of those has a corresponding y tree. So the overall space will be n log n. We're repeating points here. But the good news is now I can do search really efficiently, well, log squared efficiently. I spend log time to find these x trees that represent the slabs that I care about. So it's more like this picture. So there's a bunch of disjoint slabs which together contain my points in x. And now I want to filter each of them by y. So for each of them, I jump over to y space and do a range query in y space, just like what we were doing here. So search for A, search for B, but in y coordinate. And then I get log n subtrees in here, log n subtrees in here, log n subtrees in here. So the query gives me log squared y subtrees. Takes me log squared n time to find them. If I have subtree sizes, I compute the number of matches in log squared n time. If I want k items, I can grab k items out of them in order k time. Okay, pretty easy. Of course, d dimensions is just the same trick. You have x tree, every subtree links to a y tree, every y subtree links to a z tree, every z subtree links to a w tree, and so on. Okay, for d dimensions, you're going to get log to the d query, as I claimed before. How much space? Well, every dimension you add adds another log factor of space. So it's going to be n log to the d minus 1 space. And if you want to do this statically, you can also build the data structure in n log to the d minus 1 n time, except for d equals 1 where you need n log n time to sort. But as long as d is bigger than 1, this is the right bound for higher dimensions. So it takes a little bit of effort to actually build the structure in that much time, but it can be done. Okay, that's the very simple data structure. Any questions about that before we make it cooler? So you may have seen this data structure before. It's kind of classic, but you can do much better. Well, at least a log factor better. Yeah.
So when you say that, when you're storing one pointer for each subtree, you're essentially like have a pointer for each root, like for each node.
Yeah, right. Every node. So I know these are the nodes that the stuff below them represents my answer in X, and so I teleport over to the Y universe from the X universe.
So it's basically, it has all of the same nodes of that subtree, but
Yeah.
arranged in Y.
All the points that are in here also live in here, except these ones are sorted by X, these ones are sorted by Y. If I kept following pointers, I get to Z and W and so on. Yep. Other questions? Yeah?
So if we were doing a dynamic case, how would we implement rotations in the X?
Okay, dynamic. Dynamic is annoying. Yeah, rotations are annoying. I think we'll come back to that. We can solve that. I thought it was easy, but you're right. Rotations are kind of annoying. And we can solve it using this dynamization trick, so we don't have to worry about it till we get there. It's going to get even harder to make things dynamic, and so then we really need to pull out the black box. Well, it's not a black box. We're going to see how it works, but it's a general transformation that makes things dynamic. Okay. Before we get to dynamic, stick with static, and let's improve things by a log factor. This is an idea called layered range trees. It's also sometimes called fractional cascading, which is the technique we're going to get to later. I would say it involves one half of fractional cascading. Fractional cascading has two ideas, and the one that it's named after is not this idea. So idea one is basically to reuse searches. The idea is we're searching in this subtree, or I guess this subtree with respect to y. We're also searching for the same interval of y in this subtree. Completely different elements, but if there's some way we could reuse the searches for y in all of these log n subtrees, we could save a log factor. And it turns out we can. And this is one idea in fractional cascading, but there will be another one later. Okay. So, fun stuff. This is where I want to change my notes. So, we're searching in X with a regular 1D range tree. I also want to have a regular 1D range tree. Range tree? Sure. Actually, it doesn't matter too much. I want to have an array of all the items sorted by y coordinate. And we're going to simplify things here. Instead of pointing to a tree, I'm going to point to an array sorted by y. This is totally static. And this is where dynamic gets harder. Not that we know how to do it over there yet. So for each x subtree, we're going to have a pointer to the same elements sorted by y. Okay, so all the leaves that are down here are basically also up there, but by y coordinate instead of x. Okay, obviously we can still do the same thing we could do before. Spend log n time to search in each of these log n arrays corresponding to these log n subtrees, and in log squared n we'll have our answers. But we can do better now. I only want to do one binary search in y, and that will be at the root. So the root, there's an array representing everything sorted by y. I search for the lower y coordinate. I search for the upper y coordinate. Some things. It's hard to draw this because it's in the dimension orthogonal to this one. I guess I should really draw the arrays like this. So this guy has an array. We find the upper and lower bounds for the y coordinate in the global space. This takes log n time to do two searches. Question?
So those are the upper lower bounds from the predecessor
From
and successor queries.
Yeah, right. So we're doing a predecessor and successor search, let's say, in this array. Binary search, we find we want to do, I didn't give them names, but in the notes they're A1 through A2, through B1 in X, and they're A2 through B2 in Y. So that's my query. It's this rectangle. I'm doing the search for A2 and for B2 in the top array. Now what I'd like to do is keep that information as I walk down the tree. Okay, so that in the end, when I get to these nodes, I know where I am in those arrays in Y. So let's think of that just step by step. So imagine in the X tree, I'm at some node, and then I follow, let's say, a right pointer to the right child. Okay, now in Y space, maybe I should switch to red for Y space. This guy has a really big array representing all of the nodes down here, but sorted by Y coordinate. This guy has a corresponding array with some subset of the nodes. Which subset? The ones that are to the right of this X coordinate. So there's no relation. I mean, some of the guys that are here, let me circle them. Some of these guys exist over here. They'll be in the same relative order. So here's those 4 guys, and then 1 and 2. So some of these guys will be preserved over here. Some of them won't because their X coordinate is smaller. It's an arbitrary subset. These guys will also live here. Okay? The idea is store pointers from every element over here to, let's say, the successor over here. Okay, so store these red arrows, but also store, let's say, these guys all point to this node. These guys all point to that node. I guess these guys just point to some adjacent node, either the predecessor or the successor. So the result is, if I know where A2 and B2 live in this array, I can figure out where they live in this array. I just follow the pointer. Easy. Done. Okay, let's think about what this means. So I'm going to store pointers from the Y array of some X node. Let's call that node V in the X tree, to the corresponding places corresponding points, let's say, in the Y arrays of left of V, the left child of V, and the right child of V. So actually every array item is going to have 2 pointers, one if you're going right in the X tree, one if you're going left in the X tree. But we can afford a constant number of pointers per node. So only increases space by a constant factor. And now it tells me exactly what I need to know. I start at the root. I do a binary search. That's the slow part. I spend log n time, find those 2 slots. Every time I go down, I follow the pointer. I know exactly where A2 and B2 live in the next array. In constant time, as I walk down, I can figure this out. I can remember the information on both sides here. And every time I go to one of these subtrees, I know exactly where I live in, it's no longer a tree, now in that array. So I can identify the regions in these arrays that correspond to these matching subrectangles with no extra time. So I save that last log factor. If you generalize this to d dimensions, it only works in the last dimension. You can use this trick in the last dimension and improve from log to the d query to log to the d minus 1. In the higher dimensions, we just use regular range trees. And when we get down to the 2-dimensional case, it's a recursion. Before we were stopping at the 1-dimensional case, we use a regular binary search tree. Now we stop at the 2-dimensional case, and we use this fancy thing. I call this cross-linking. A lot of people call it fractional cascading. Both are valid names. It's a cool idea. but simple once you can see both dimensions at once, which I know it's hard to see in 2 dimensions, but it can be done. All right. Questions? I guess the obvious question is dynamic. Now we're going to go to dynamic. This is a very static thing to be doing. How in the world would we maintain this if the point set is changing? All these pointers are going to move around. Life seems so hard. But it's not. In fact, updates are a lot easier than you might think. Some of you may believe this in your heart. Some of you may not. But if you've ever seen an amortization argument that says basically when you modify a tree, only a constant number of things happen, and they usually happen near the leaves. Think of a binary search tree. The easiest way to see it is in a B tree, if you know B trees. Usually you do maybe, if you do an insertion, you're going to do maybe 1 or 2 splits at the bottom, and that's it. Constant fraction of time, that's all there is. So it should only take constant time to do an update. This structure is easy to update at the leaves, because at the leaves, if you look at one of these structures, a constant number of items, there's a constant size array, you could update everything in constant time. If we're only updating near the leaves, then life is good. Occasionally, though, we're going to have to update these giant structures, and then we're going to have to spend giant time. That's okay. The only thing we need out of this data structure is that it takes the same amount of space and preprocessing time. N log to d minus 1 space and time to build this static data structure. If we have this, it turns out we can make it dynamic for free. This is the magic of weight balance trees. In general, there are many kinds of weight balance trees. We're going to look at one called BB alpha trees, which are the oldest and sort of the simplest. And